Dear students, you certainly have heard of earthquakes and have an idea on how earthquakes can be massive destroyers. About 15,000 people are killed by them every year, and more than 100 million people have lost their lives due to earthquakes in the history of mankind. Earthquakes have the power to uproot trees and buildings. They can trigger landslides and avalanches, resulting in fires, flooding, and tsunami that cause further devastation. To explain in geological terms, an earthquake is the consequence of a sudden release of energy in the Earth's crust. This outburst of energy from the Earth's crust produces seismic waves. During an earthquake, two blocks of the earth suddenly slip past one another. The surface where they slip is called the fault or fault plan. Earthquakes occur most often along the geological faults, narrow zones where rock masses move in relation to one another. The major fault lines of the world are located at the fringes of the huge tectonic plates that make up the Earth's crust. In this chapter, we will discuss about the recent earthquakes in India and also focus on Indian tectonic plate, seismic zones of India, tectonic earthquakes, prominent recent earthquakes in India, future programs on earthquake geology. The India or Indian plate is a tectonic plate that was originally a part of the ancient continent of Gondwana land from which it split off, eventually becoming a major plate. About 50 to 55 million years ago, it fused with the adjacent Australian plate. It is today part of the major Indo Australian plate and includes the subcontinent of India and a portion of the basin under the Indian Ocean. About 90 million years ago, subsequent to the splitting off from Gondwana land, the India plate split from Madagascar. It began moving north at about 20 centimeter per year and began colliding with Asia between 50 and 50 million years ago. During this time, the India plate covered a distance of 2000 to 3000 kilometers and moved faster than any other known plate. In 2007, German geologists determined that the reason the India plate moved so quickly is that it is only half as thick as the other plates which formerly constituted Gondwana land. The collision with the Eurasian plate along the boundary between India and Nepal formed the orogenic belt that created the Indian plateau and the Himalayan mountains as sediment bunched up like earth before a plow. India lies at the northwestern end of the Indo Australian plate, which encompasses India, Australia, a major portion of the Indian Ocean, and other smaller countries. This plate is colliding against the huge Eurasian plate and going under the Eurasian plate. Three chief tectonic subregions of India are the mighty Himalayas along the north, the plains of the Ganges and other rivers, and the peninsula. The Himalayas consist primarily of sediments accumulated over long geological time in the Tethys. The Indo-Gangetic basin with deep alluvium is a great depression caused by the load of the Himalayas on the continent. The peninsular part of the country consists of ancient rocks deformed in the past Himalayan-like collisions. Erosion has exposed the roots of the old mountains and removed most of the topography. The rocks are very hard but are softened by weathering near the surface. Before the Himalayan collision, several tens of millions of years ago, lava flowed across the central part of the peninsular India, leaving layers of basalt rock. Coastal areas like Kutch show marine deposits testifying to submergence under the sea millions of years ago. Formation of Himalayas. The highest mountain range in the world, the snow capped Himalayas, is an example of a continent to continent collision. This immense mountain range began to form when two large landmasses, India and Eurasia, driven by tectonic plate movement, collided. As both landmasses have about the same rock density, one plate could not be subducted under the other. The pressure of the colliding plates could only be relieved by thrusting skyward. The folding, bending, and twisting of the collision zone formed the jagged Himalayas peaks. This string of towering peaks is still being thrust up as India, embedded in the Indo Australian plate, continues to crunch relentlessly into Tibet on the southern edge of the Eurasian plate. The India plate is currently moving northeast at 5 centimeter per year, while the Eurasian plate is moving north at only 2 centimeter per year. This is causing the Eurasian plate to deform and India plate to compress at a rate of 4 millimeter per year. The Geological Survey of India (GSI) first published the seismic zoning map of the country in the year 1935. With numerous modifications made afterwards, this map was initially based on the amount of damage suffered by the different regions of India because of earthquakes. The varying geology at different locations in the country implies that the likelihood of damaging earthquakes taking place at different locations is different. Thus, a seismic zone map is required to identify these regions. Based on the levels of intensities sustained during damaging past earthquakes, the 1970 version of the zone map subdivided India into 5 zones: first, second, third, fourth, and fifth. The maximum modified Mercalli mm intensity of seismic shaking expected in these zones were 5 or less, 6, 7, 8, and 9, and higher, respectively. Parts of Himalayan boundary in the north and northeast, and the Kutch area in the west were classified as Zone 5. The seismic zone maps are revised from time to time as more understanding is gained on the geology, the seismotectonics, and the seismic activity in the country. The Indian standards provided the first seismic zone map in 1962, which was later revised in 1967 and again in 1970. The map has been revised again in 2002 and it now has only 4 seismic zones: 2, 3, 4, and 5. Zone 2, least active seismic zone. Zone 3, moderate seismic zone. Zone 4, high seismic zone. Zone 5, highest seismic zone. The areas falling in seismic zone 1 in the 1970 version of the map are merged with those of seismic zone 2. Also, the seismic zone map in the peninsular region has been modified. Chennai now comes in seismic zone 3 as against in zone 2 in the 1970 version of the map. This 2002 seismic zone map is not the final word on the seismic hazard of the country, and hence there can be no sense complacency in this regard. This kind of map is mainly used by the Department of Disaster Management of the different state governments in the country. This map helps them in planning for a natural disaster like earthquake. An Indian seismic zoning map assists one in identifying the lowest, moderate, as well as highest hazardous or earthquake prone areas in India. Even such maps are looked into before constructing any high rise building so as to check the level of seismology in any particular area. This in turn results in saving life in the long run. As we learned before, earthquakes are caused by the sudden release of energy within some limited region of the rocks of the earth. The energy can be released by elastic strain, gravity, chemical reactions, or even the motion of massive bodies. Of all these, the release of elastic strain is the most important cause because this form of energy is the only kind that can be stored in sufficient quantity in the earth to produce major disturbances. Earthquakes associated with this type of energy release are called tectonic earthquakes. Tectonics. Tectonic earthquakes are explained by the so called elastic rebound theory formulated by the American geologist Harry Fielding Reid after the San Andreas Fault ruptured in 1906, generating the Great Earthquake. According to the theory, a tectonic earthquake occurs when strains in rock masses have accumulated to a point where the resulting stresses exceed the strength of the rocks and sudden fracturing results. The fractures propagate rapidly through the rock, usually tending in the same direction and sometimes extending many kilometers along a local zone of weakness. As a fault rupture progresses along or up the fault, rock masses are flung in opposite directions and thus spring back to a position where there is less strain. At any one point, this movement may take place not at once but rather in irregular steps. These sudden slowing and restarting give rise to the vibrations that propagate as seismic waves. Such irregular properties of fault rupture are now included in the modeling of earthquake sources, both physically and mathematically. Roughness along the fault is referred to as asperities, and places where the rupture slows or stops are said to be fault barriers. Fault rupture starts at the earthquake focus, a spot that in many cases is close to 5 to 15 km under the surface. The rupture propagates in one or both directions over the fault plan until stopped or slowed at a barrier. Sometimes, instead of being stopped at the barrier, the fault rupture recommences on the far side. At other times, the stresses in the rocks break the barrier and the rupture continues. Earthquakes have different properties depending on the type of fault slip that caused them. The usual fault model has a strike, that is, a direction from north taken by a horizontal line in the fault plan, and a dip, the angle from the horizontal shown by the steepest slope in the fault. The lower wall of an inclined fault is called the footwall. Lying over the footwall is the hanging wall. When rock masses slip past each other parallel to the strike, the movement is known as strike slip faulting. Movement parallel to the dip is called dip slip faulting. Strike slip faults are right lateral or left lateral, depending on whether the block on the opposite side of the fault from an observer has moved to the right or left. In dip slip faults, if the hanging wall block moves downward relative to the footwall block, it is called normal faulting. The opposite motion with the hanging wall moving upward relative to the footwall produces reverse or thrust faulting. All known faults are assumed to have been the seat of one or more earthquakes in the past, though tectonic movements along faults are often slow and most geologically ancient faults are now seismic. That is, they no longer cause earthquakes. The actual faulting associated with an earthquake may be complex, and it is now not clear whether in a particular earthquake the total energy issues from a single fault plan. Observed geologic faults sometimes show relative displacements on the order of hundreds of kilometers over geologic time, whereas the sudden slip offsets that produce seismic waves may range from only several centimeters to tens of meters. A number of significant earthquakes occurred in and around India over the past century. Some of these occurred in populated and urbanized areas and hence caused great damage. Many went unnoticed as they occurred deep under the earth's surface or in relatively uninhabited places. Most earthquakes occur along the Himalayan plate boundary. These are interplate earthquakes, but a number of earthquakes have also occurred in the peninsula region. These are intraplate earthquakes. Four great earthquakes occurred in a span of 53 years from 1897 to 1950. The January 2001 Gujarat earthquakes is almost as large. Each of these caused disasters has allowed to learn about earthquakes and to advance earthquake engineering. For instance, 1890 Ran of Kutch earthquake, magnitude of 8.2, produced an unprecedented and approximate 3 meters high uplift of the ground over 100 kilometers called Allaband. The 1897 Assam earthquake, magnitude 8.1, caused severe damage up to 500 kilometers radial distances. The type of damage sustained led to improvements in the intensity scale from 1 to 10 to 1 to 12. Extensive liquefaction of the ground took place over a length of 300 kilometers called the slump belt. During 1934, Bihar Nepal earthquake, magnitude 8.7, in which many structures went afloat. Some of the damaging and more recent earthquakes are listed here. Date September 18, 2011. Location and details: Gantok, Sikkim strong earthquake in northeast India. Tremors felt in Delhi, Kolkata, Lucknow, and Jaipur. Deaths 118, magnitude 6.9. October 8, 2005. Kashmir, 95 kilometers northeast of Islamabad, Pakistan, 125 kilometers WNW of Srinagar, Jammu and Kashmir, and India. Deaths 130,000, magnitude 7.6. December 26, 2004, off west coast northern Sumatra, India, Sri Lanka, and Maldives. Death rate would be 283,106, magnitude 9.3. January 26, 2001, location Gujarat. The death rate would be 20,000, magnitude is 7.6 or 7.7. Here are the highlights of each of these significant recent earthquakes which have occurred in India. 2011 Sikkim earthquake. The magnitude 6.9 earthquake occurred inland at 1810 Indian Standard Time on 18th September 2011, about 68 kilometers northwest of Gantok, Sikkim, at a shallow depth of 19.7 kilometers. At its location, the continental Indian and Eurasian plates converge with one another along a tectonic boundary beneath the mountainous region of northeast India near the Nepalese boundary. Although earthquakes in this region are usually interplate in nature, preliminary data suggest the Sikkim earthquake was triggered by shallow strike slip faulting from an intraplate source within overriding Eurasian plate. Initial analysis also indicate a complex origin, with the perceived tremor likely being a result of two separate events occurring close together in time at similar focal depths. The strongest shaking occurred to the west in Gantok and further south in Siliguri, although similar ground motions registering at modified Mercalli mm 6 strong on the Mercalli scale were recorded in many smaller towns such as Mangan across elevated regions. Lighter tremors mm 4 to 3 spread southward through populous regions, with these motions reported in the Patna, capital of Bihar, and as far southwest as Bihar Sharif. 2005 Kashmir earthquake. Kashmir lies atop a network of active geological faults with underground dynamics that challenge the complexities above ground. Kashmir lies on the boundary of two colliding tectonic plates: the small Indian plate that underlies most of India and Pakistan, including much of Kashmir, and the vast Eurasian plate that underlies Europe, China, Russia, and much of the Middle East. The source of the 8 October 2005 earthquake of M7.6 was the northwest striking Balakot Bhag BB fault. It registered a moment of magnitude of 7.6 centered in the Pakistan administered Kashmir near the city of Muzaffarabad, also affecting the Khyber Pakhtunkhwa province of Pakistan. This surface rupture extended for 75 kilometers, which is 47 miles, and was a first among earthquakes in the Himalaya seismic zone. Two towns that straddled the newly exposed fault suffered the most damage, Muzaffarabad and Balakot. 2004 Indian Ocean earthquake. The earthquake was caused when the Indian plate was subducted by the Burma plate and triggered a series of devastating tsunamis along the coast of most landmasses bordering the Indian Ocean, killing over 230,000 people in 14 countries and inundating coastal communities with waves up to 30 meters, which is 100 feet. It was one of the deadliest natural disasters in recorded history. Indonesia was the hardest hit country, followed by Sri Lanka, India, and Thailand. With a magnitude of MW 9.1 to 9.3, it is the third largest earthquake ever recorded on a seismograph. The megathrust earthquake was unusually large in geographical and geological extent. An estimated 1,600 kilometers, which is 1,000 miles, of fault surface slipped or ruptured about 15 meters, that is 50 feet, along the subduction zone where the Indian plate slides under the overriding Burma plate. The Indian plate is part of the Great Indo-Australian Plate, which underlies the Indian Ocean and Bay of Bengal and is drifting northeast at an average of 6 centimeters per year, that is 2.4 inches per year. The India Plate meets the Burma Plate, which is considered a portion of the Great Eurasian Plate at the Sunda Trend. At this point, the India Plate subducts beneath the Burma Plate, which carries the Nicobar Islands and the Andaman Islands, and also northern Sumatra. The India Plate sinks deeper and deeper beneath the Burma Plate until the increasing temperature and pressure drive volatiles out of the subducting plate. These volatiles rise into the overlying plate, causing partial melting and formation of magma. The rising magma intrudes into the crust above and exits the Earth's crust through volcanoes in the form of volcanic arc. The volcanic activity that results as the Indo-Australian plate subducts the Eurasian plate has created the Sunda arc. As well as the sideways movement between the plates, the seafloor is estimated to have risen by several meters, displacing an estimated 30 cubic kilometers of water and triggering devastating tsunami waves. The waves did not originate from a point source, as was inaccurately depicted in some illustrations of their paths of travel, but rather radiated outwards along the entire 1,600 kilometers length of the rupture, acting as a line source. This greatly increased geographical area over which the waves were observed, reaching as far as Mexico, Chile, and the Arctic. The raising of the seafloor significantly reduced the capacity of the Indian Ocean, producing a permanent rise in the global sea level by an estimated 0.1 millimeters. 2001 Gujarat earthquake. Gujarat lies about 400 kilometers from the plate boundary between the Indian plate and the Eurasian plate, but the current tectonics is still governed by the effects of the continuing continental collision along this boundary. During the breakup of Gondwana in the Jurassic, this area was affected by rifting with a roughly west-east trend. During the collision with Eurasia, the area has undergone shortening, involving both reactivation of the original rift faults and development of new low angle thrust faults. The related folding has formed a series of ranges, particularly in central Kutch. The focal mechanism of most earthquakes is consistent with reverse faulting on reactivated rift faults. The pattern of uplift and subsidence associated with the 1890 Rann of Kutch earthquake is consistent with reactivation of such a fault. The 2001 Gujarat earthquake was caused by movement on a previously unknown south dipping fault trending parallel to the inferred rift structures. The Disaster Management Act, which is also called as DM Act 2005, lays down institutional and coordination mechanism for effective disaster management at the national, state and district levels. The critical areas of concern for the management of earthquake in India include the lack of awareness among various stakeholders about the seismic risk, inadequate attention to structural mitigation measures in the engineering education syllabus, inadequate monitoring and enforcement of earthquake resistant building codes and town planning bylaws, absence of systems of licensing of engineers and masons, lack of formal training among professionals in earthquake resistant construction practices, lack of adequate preparedness and response capacity among various stakeholder groups. Estimating the extent of damage to life and property in the event of an earthquake is required so that suitable disaster management strategies can be evolved. Rehabilitation programs, reconstructing houses, a school, and rural education centers damaged or destroyed by the earthquake, restoring livelihoods through the protection and management of local natural resources, strengthening healthcare systems to improve access and the range of quality of essential services, introducing water supply and sanitation systems in villages, empowering village based institutions and other agencies through training programs to plan and manage equitable and participatory rehabilitation processes as well as initiate disaster preparedness of the community. This is important given the fact that the area is on a seismically fragile zone and further earthquakes cannot be ruled out. Documenting and disseminating lessons learned. For example, a rehabilitation program was undertaken to address the January 2006-2001 Gujarat earthquake. This program provided immediate support in the following areas: rapid post earthquake reconnaissance to assess impact and development of retrofitting techniques for damaged structures, evaluation of earthquake ground motions data, seismic hazard and vulnerability, and causes of damage, development of design guidelines for new constructions and evaluation of structural designs, training of government and private sector engineers in repairs and rehabilitation of damaged buildings, providing technical inputs to the World Bank and Asian Development Bank for framing their emergency loan packages, assisting the government of Gujarat with framing of rehabilitation policy of the state, preparation of redevelopment plan for the town of Anjar in Gujarat to ensure seismic safety as well as sustainable development, assisting in design and construction of earthquake memorial in Anjar in memory of the school children and their teachers who died during Republic Day parade.